Hi, today we're going to talk about something that violates the octet rule when we are doing a Lewis structure. And then I'll show you how to draw the shape of it. And we'll talk a little bit about some other things later on that violate the octet rule in other ways. So the first thing we're going to talk about is boron trichloride. Now, when we write that out, we know that this is treated as a covalent compound because it's got the prefix chloride. Okay, so then all I have to do is I'm checking my electronegativities, and boron comes out at a 2.04 and chlorine comes at a 3.16. Okay, and so all I have to do is take 3.16 minus 2.042. Now, that's a pretty polar bond because it's a 1.12, but it's not polar enough to be a ionic bond. Okay, so even though boron is there and aluminum's right below it, and so we might think this is a metal. This actually works as a non-metal, boron does. And when it forms covalent compounds, it has 3 valence electrons, so it's happy just making 3 bonds, okay? And so my boron, as stated, has 3 valence electrons. I've got one of those, so that's 3 electrons. My chlorine, it has 7, and I've got 3 of those, so that's 21, and so I've got 24 total electrons. So that's how we figure that one out. So boron is 3, okay, and then chlorine, 7 times 3 is 21, 3 and 21 is 24. There's no charge or anything up here, so I got 24 electrons to put out on the playing field here. So I know that boron has to be my central because chlorine can only make 1 bond. And so what I'm going to do is I'm going to put the chlorine around it, okay? Now, that's about as far apart as those chlorines can be. So if you think about it, if you move this stick farther away from this one, it gets closer to this one. So this is actually as far apart as they can be. And notice that flat, 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 they all lay flat on the ground, okay? And then I'm going to put on my chlorine. And so I use 2, 4, 6 to attach my chlorine. And so I have 18 left. So I use 2, 4, 6, I have 18 left. Now, my chlorine, it needs 2, 4, 6. 1, 2, 3, 4, 5, 6. The other one also needs 6. And the other one needs 6. So 6, 6, 6. And when I do that, 2, 4, 6, 2, 4, 6, 2, 4, 6. 6 times 3 is 18. 18 minus 18 is 0. And so we're ready to go. This is a good structure. Now, you might ask, what does this structure look like in the real world, okay? And this is the same way, okay? This is how it looks because this is as far apart as these 3 things can be, and that's what the attached atoms want to be, is they want to arrange themselves so they're as far apart as possible. And if you actually make this structure, you'll find no matter how you bend it, and you can make it just by doing something, like this. And then when you bend, either one of them, you're going to find that it starts to get closer to one or the other. Even if you go forward or backward or to the side, it doesn't matter. Okay, I know it's not exactly 120, but if you move any one of these, the best they can be is 120 degrees apart and flat. And so that's the actual geometric shape too. So the angle is 120 degrees, and we call that trigonal, which essentially means triangle. Trigonal planar, which means that, get my fancy thing here together again. So when we do that, see, it all sits, had to drop it, didn't I? But it all sits in the plane. So this violates the octet rule in that boron only wants 2, 4, 6. Boron's really the only common element that you're ever going to have to make a Lewis structure for that violates the octet rule with less than 8. Maybe you'll see a beryllium, but this is the one that they pull out on you like regular. So anyway, have a good day. Catch you later.